Okay. So, hi everyone. I'm going to talk about probabilistic evaluation of deep generative models, more specifically a paper I did jointly with Fernando on optimization of the sampling algorithm that we can use for evaluation of latent variable models. So to give you a general overview, many of the generative models are trained based on fitting an unnormalized density function to some distribution of the random variable of our interest. So we have an implicit density function phi, which we can only compute up to a normalization factor. And the normalization factor is in general intractable in high dimensions. And well, it is what we call the likelihood, and we need to evaluate the model using that to say if the model is covering the data distribution right. The general solutions for that are using methods like sampling, which means that we use MCMC chains, need a lot of steps for convergence and is time consuming. We can also approximate the target distribution with variational approximations using some density function that is actually tractable and we can easily sample from, or use a combination of both of these methods to have a more complex variational approximation of the target distribution. The method that I'm going to talk about is the third category. So annual importance sampling is an approximate sampling method that gives us importance weights to correct for the inaccuracy in the sampling process. The way that it works is that we extend the space of the random variable. We practically sample trajectories starting from the, we don't sample this, but we consider the process of in this extended space that starts from the target distribution and follows some Markov transition kernels to go backwards in time. And we consider the simpler forward process in time, which starts from an initial tractable distribution and follows other Markov transition kernels to actually sample trajectories first. Using these two definitions, and we have to choose these two processes. And after choosing them, we can compute the corresponding weight to each one of the sample trajectories by using the ratio of the extended target distribution density to the actual sampling distribution that we are using. And our estimation of the normalization factor is going to be equivalent to the average of mean of the importance weights, or we can estimate it with Monte Carlo method. So we generally want our final particles that come from the sequential sampling process to be as close as we can to the target distribution. The way that annual importance sampling handles this is by defining an annealing density path, which is denoted here by gamma, and it changes from the initial distribution when t is 0, goes all the way to the target density, the unnormalized target density at t equal to 1. And for each fixed t, this is giving you an unnormalized density over the random variable c. And we also need a discretization schedule for this in order to look at each one of the distributions in discrete time and be able to do the Markov transitions between each consecutive distribution. So ideally, after choosing all of these hyperparameters, we want to find some transition kernels that can actually sample exactly from each one of the annealing distributions. And if we can do this, and we choose the conditionally reverse process of sampling to trace back the trajectories to the initial distribution, we can minimize the variance of the estimation and have optimal estimation in this way. But the ideal case doesn't happen very often. And what we see in the literature is that there are either parametric ways of definition of these transition kernels. Separately, we have to choose an architecture for the forward and for the backward transition kernels. They usually do this with Gaussian mixtures or normalizing flows, which are complex. Or there is another way, after fixing the annealing density path, which we use reversible transition kernels with respect to each one of the densities that we have in our chain. And the reversal of these transition kernels can be used as the kernels that we have for the backward process. The problem with this is that the backward transition kernels are not exactly similar to the conditionally reversed forward transition kernels. So we need a large number of annealing distributions, and also we need to optimize the schedule of discretization to make sure that each two consecutive distributions are not changing very drastically. Instead of focusing on the transition kernels and optimizing that, we propose a different method to optimize the annealing density path in AIS algorithm. So in our method, we parameterize this density path in a log space using a heuristic that is commonly used, the geometric mean between the initial distribution and the target distribution densities. And our neural network is learning the residual term of density with respect to this geometric mean. And we also have some extra terms to make sure that the endpoints of our annealing sequence are correctly set when t is equal to 0 or 1. By setting this parameterization for our annealing density path, we can share actually parameters between intermediary densities, which is different from the way that people usually approach parameterization of sampling algorithms, which is by having separate parameters for each one of the transition kernels that they're using. And also, if the neural network that we are using is expressive enough, there is no need to optimize the schedule, because implicitly it can represent every different schedule if we only consider the linear spacing between the time. In cases that we have a context conditional sampling problem like latent variable models, we want to have multiple model sampling algorithms that we have optimized for different contexts at the same time. We can actually amortize the training cost over all of this by conditioning the neural network and also the densities that we have on the observation. So this happens in latent variable models, and this is the main advantage of our method, because otherwise the training time would take so long, it wouldn't make sense to have shorter sequences of annealing, but still have the training time in advance. In comparison to just having the longer sequences of annealing, which are actually very accurate. So for the optimization objective, we have considered all the measures that they use in literature for tuning or training AIS parameters. And I'm going to talk about each one of them separately. So effective sample size is asymptotically is supposed to give the variance between having the estimation using the sampling process that we are using and the variance of the estimation when the samples are coming from the target distribution, and is able to detect weight degeneracy. The weight degeneracy problem happens in the sequential sampling algorithms when most of the particles have weights close to 0 and they don't contribute to the estimation that we are doing. Only a few particles are actually active in the estimation. So this is actually a good metric, but we can only use this for tuning purposes, because when effective sample size is high, we don't know if the variance of the importance weights are low because they are not sufficiently dispersed. They are all coming from the same region, and the importance weights are all similar to each other, or if the particles are actually sufficiently dispersed and they have reached high density places and they still have similar weights. So in the first phase of the optimization, it is difficult to use this because the forward process in AIS is not similar to the target process, and most of the particles are still focused in the same region. The other optimization objective that we actually are considering is bidirectional Monte Carlo gap, which was recently in the last few years proposed to assess how well the sampling algorithm is able to evaluate the estimate expectations for over-unnormalized sensitive function. And it is equivalent to the Jeffreys divergence. We can show, we later show in the plots that it is empirically trading off between the estimation bias and variance. But in order to evaluate this, the first term requires samples from the target X and the target distribution, which we don't have. We can estimate the first part using particles from AIS and the importance weights, but when we do gradient-based optimization, it produces two contending terms that cancel each other almost all the way. So practically in high dimensions, it becomes very noisy and unstable to train with the gradients that we get from this loss. But in lower dimensional cases, it works fine. The other loss that we are considering is inverse scale divergence loss, which generally is used in variational inference. It upper bounds the estimation bias, and recently was shown that it can approximate a scaled version of the variance of the importance space if the sampling process is sufficiently regular. So the next step that we have to consider is the gradient estimation step with respect to the losses that we have. And the transition kernels that we are using are reversible transition kernels, which use metropolis hasting accept reject step, which makes them practically not continuous with respect to the Lebesgue measure. We can partially reparameterize these transition kernels using a bijective function of the previous state of the particles and some independent variable that represents the step that we are taking in each step, conditioned on the fact that this step is being accepted or not. But for the part of the distribution that depends on the density of acceptance or rejection, we can do reparameterization. Most of the literature just forgets about the score function estimation for that part, says that the bias is not important for the training and the results are similar when they do optimization without it. But for our case, in high dimensionals, we observe that it is necessary to have a unbiased estimation of the gradient. So we use star function with control variables to reduce the variance of that part. So to show some of the results that we have in two-dimensional benchmark data distributions, the target distributions are the top row of that plot in the right. And our algorithms, inverse scale divergence and the bidirectional or the gap minimization on the last two rows, we can see that our algorithm is able to cover a larger part of the support of the target distribution when the distribution is ill-defined actually and ill-conditioned. And the colors show how, when the colors are red, it means that the weight of those particles are larger. So in the bidirectional multivariate gap optimization, the variance of the colors are smaller. It means that most of the particles have similar weights and they contribute to the estimation to the same way. The plot on the right shows estimation bias, log variance of the importance weights and bidirectional gap to show how well our sampling method is estimating the test function and the normalization constant. And the last one shows the correlation between bidirectional gap and some of the bias and variance, which shows the trade-off that it is naturally doing. So we have run our algorithm for multiple different transition kernels. We use random walk, Hamiltonian Monte Carlo, and MALA. And we compare it to ordinary not optimized AIS algorithm with different schedules and different annealing paths. The top ones in the I'm not sure if you can see the colors, but the top ones in the bias plot are usually the parametric ones, and they show that we can estimate the normalization factor more accurately when the number of annealing steps are actually low, which is when we are working in a low computational budget scheme. And in this plot, we see that with the plots are a bit crowded, but we can see that most of the parametric optimization that we have done with bidirectional Monte Carlo gap minimization have lower variance in comparison to the inverse scale divergence. So the last part of the results that I want to show is over genetic models that are trained on this data set. We have VAE importance, the weighted autoencoder, generative adversarial network, and bidirectional GAN, which all use the same decoder network. They have very different auxiliary networks to be trained. And the first plot shows the sample reconstruction using optimized path and important sampling in the last row. The results of reconstruction are not perfect like the encoders of the networks, but they are similar to the results that we can get from another sampling algorithm with 1024 annealing distributions and 16 times more complex transition kernels. So I would say the results are comparable. And in the table, we showed the negative likelihood estimation using the optimized path AAS with 8 and 16 annealing distribution, which shows the results are still comparable and sometimes improve over the more complex version of annealing importance sampling, and have lower variance in comparison. But the thing that I want to mention, it is worth noting, is that the last column shows the ground truth normalization factor that we should be estimating. Actually, I'm using a more exhaustive version of sampling methods to estimate this part, and we are still very far off from that. So using in a low budget scenario, the computational budget scenario, it is not enough to just use reversible transition kernels to achieve that. So in conclusion, we have proposed a method to optimize the annealing density sequence in the AIS algorithm using the residual part of the density in comparison to popular heuristics, and by doing variance reduction and amortizing the training overhead of invariant variable models. And we have been able to have comparable results to a more complex version of the algorithm and improve over it. And there is a short discussion that I want to make about probabilistic model evaluation, which is a method that is generally used for training and for evaluation, choosing a model selection or model comparison. It shows good results, but it is not perfect. And there are some works that show that it can be independent of the quality of the samples that the model is able to generate. So when the normalization log likelihood, when the negative log likelihood is low, it means that the model is not actually covering the data distribution very well. But when it's high, we cannot just say the model is right. We have to use it together with other sample quality measure scoring tools, like the ones that depend on specific applications, or the ones that are more commonly used in a wider range of distribution, data distribution. So thank you for listening. Question.
Going back to the last slide about the discussion on the, so most likely the paper by Matthias and the authors tend to say that okay, when you're in an element, all of them, the likelihood is very low.
Mm-hmm.
So if the bad likelihood is very bad,
Mm-hmm.
why take the best of the worst? It doesn't need to be a two. And this is why they need all the other options. Again, none of it.
Yeah, they are also not perfect. You have to have some kind of different trade-off between what you prefer in your generative model, if you want to have more realistic samples or if you want to have a better likelihood estimation. It depends on the application of the generative model for generation or for inference, or what you're using it for. So, no more questions.
Salman, it's you now.
Yeah. Okay.
It's a bit. I think that you can do. Do you have? Does she has directly a?
It's HDMI.
It's HDMI directly.
Yeah. Maybe.
No.
Yeah, I'm trying here. I don't join this way. Yeah, because
It used to work though. No, that's the charger.
okay. Okay. Yeah. Okay. Hello, everybody. My name is Salman Muhibbi from University of Padua. Today, I'm going to talk about some chapters of my dissertation about resource allocation in self-massive MIMO systems. Starting from first to the fifth generations of the cellular network, the massive traffic growth in traffic demands has been managed by employing several ideas and technologies, like us exploring higher frequency rates, like as millimeter wave, or refining the current and existing radio interfaces, and the other one is network densification. This densification can happen in two different ways, either by increasing the number of antenna elements at the base station or per site, which is already known as massive MIMO. And the other one is by deploying smaller and smaller cells, also known as ultra-dense networks. Both of these densification schemes suffers from some shortages. The first one suffers from the large quality of service variation because of the large distance between the base stations and the users that are located at the edge of the cell. And the other one suffers from the increased intercell interference as they are developed very densely, deployed very densely. Yeah, they are mostly, the users are located at the edge. Again, they kind of suffers from large interference, intercell interference. In the other hand, recently, self-massive MIMO systems has been proposed as an answer to these two shortages by combining of the best features of these two for above mentioned technologies. User-centric self-massive MIMO systems, or self-massive MIMO systems in general, they have composed of very large number of distributed antenna elements that's jointly trying to serve a relatively smaller number of user equipments. The operation is take place in a user-centric fashion, which means one user equipment surrounded by multiple access point and served by this access point. In comparison to traditional or conventional network-centric cellular systems, which we have a one base station that's kind of tries to serve multiple users by its own. All the user equipments, all the access points connected through some fibers, fronthaul links, to some CPUs where some network optimization, operations takes place, like synchronizations or data coding and pre-coding. The whole procedure is kind of adopts this coherent blocks model, where the time frequency intervals divided into some time frequency resources, basically divided into some intervals, where each interval is basically can be characterized by the propagation environment, whether mobility or carrier frequency and some stuff like this. Each coherence interval further divided to 3 different subintervals. At the first step, first subinterval used for uplink pilot training, the second and third used for uplink and data downlink data transmissions, which operates in a TDD fashion, basically. Here, what do we care about? Acquiring the accurate channel state information is critical for in general for massive MIMO operations, because we need to know accurate channel state information, because we are using this information to code and decode the data. So here, because of this, we need to have some sort of uplink pilot training, and we kind of skip downlink pilot training phase by considering the channel symmetry. We consider the uplink and downlink channels are basically the same. As an example, okay, we have M access points and K users. We know the number of users are relatively smaller than the number of access points. The channel between the user. Sorry, I need to do this. The channel between, for example, user equipment K and access point N are kind of shown by are kind of composed of the larger scale fading coefficient and a smaller scale fading coefficients at the same time. Okay, I told you the procedure has basically 3 different steps. In first step, in the uplink training steps, we assume we have only tau p, usually orthogonal pilot sequence. This tau p is independent from the number of user equipments and basically is smaller than the number of user equipments. And all the access points at the same time try to transmit this pilot signal to all the access points. What the access point receives, for example, as you can see here, is the combination of the signal received from all the user equipments. So by employing some MMSE estimator, access point can kind of estimate the channel between itself and a given user equipment by knowing the actual pilot, basically. On the other hand, after that, I mean, in the uplink data transmission phase, it's kind of the procedure is similar to the previous one. What happens is all the access points, all the user equipments at the same time transmit their data in the uplink. What access points receive, access point M receive is again some combination of the signal from all the users. But here we assume we kind of from previous step we estimated the channel. We have this G. What do we know? What do we need? Is kind of extracting this Q basically. This is the target signal. By employing some maximum ratio, combining a scheme, each access point can try to kind of extract a channel between for a given user, and all the users, all the access points send the data to the CPU, and then CPU by combining all the signals can kind of understand what was the signal for the given user. And this formula here basically shows the achievable uplink rate, which we used later here in this equation. Here I told you the we have some problems here. As I told you, the number of pilots, available pilots, is relatively smaller than the number of user equipments. So we need to assign same pilot to the different user equipments. And what happens here, because they are using some the same pilot, and yeah, so at the base stations, at the access point, the access point cannot kind of accurately estimate the channel between itself and the given users that are using the same pilot. We know this, we call this basically undesirable effect as a pilot contamination, and we are trying to avoid this problem. In this work, we tried to kind of solve this pilot allocation or pilot assignment problem. What we did was kind of try to kind of formulate the problem as a sum rate maximization problem, where number of users, all the users, we are trying to basically maximize the rate for all the users given different pilot vector, pilot assignment vector. And we kind of formulated this problem as a diverse or repulsive clustering problem. What do we mean by repulsive clustering? Is okay, in conventional clustering, we need to kind of maximize the similarity among the data points that are located in same cluster. But in repulsive clustering, what we are trying to do is increasing the maximizing the dissimilarity here. And this problem can be formalized as a maximally diverse clustering problem, which here, yeah, X is basically the pilot user association matrix, and F here is the repulsive measure, repulsive factor, something that shows how good our approach, how good our assignment is, kind of our clustering, basically the quality, which shows basically the quality of clustering. Solving this problem is not easy. It's a combinatorial problem, and it's proven that it's MP hard. So we need to do something else. What do we do is sort of defining a searching problem to solve this repulsive clustering problem. What we propose is a very simple algorithm. Firstly, we equally divide the users among the pilots, among the clusters, let's say. And later we pick two different clusters and two different iterate over the users. And if there is a changing the pilot of these two, kind of the cluster of these two basically user increases the our pilot our score, repulsion factor or repulsion score. We kind of exchange the pilot, and we do this exchanging until as long as the performance improves. For the simulation, I mean, we consider it M access points that's uniformly distributed in 1 square kilometers. We further use this wrapping around technique to avoid the boundary effects of the network and think the network operates as in an unlimited space, basically. And the model we used, I forgot to add it here, but it's 3GP urban macro cell models. And the diversity score or repulsion factor we used here is simply the Euclidean distance among the user equipments, as we use the location of the user as our input, basically. And here is in the table some details about the implementation setup. Okay, just as I told you, this problem is not easy to solve. Finding the optimal solution is not that easy. Just to check with optimal solutions and basically the exhaustive search, what we did is kind of for a very small scenario, we compared our result with this exhaustive search one, and also this green plot here, the green bar here shows the Oracle, algorithm or Oracle method where we consider the interference among the users 0. We assume there isn't any sort of interference.
It's not really an oracle, it's more an ideal.
Yeah, I would say. And actually, it's not ideal case because it's not possible to have, I don't know, zero interference. We need to have at least equal, I don't know, for different user equipments, we need to have the same amount of orthogonal pilots.
Right. So this is the reason why it's an ideal case, because you cannot beat the exhaustive search, right?
Yeah.
If it wasn't ideal, it would not beat the exhaustive search. The exhaustive search gives you the best
exactly
solution that you can have with practical constraints. If you do better than that,
it is not possible actually. Yeah, because of this, we're calling it Oracle, or maybe we need to call it something else.
Yeah.
But the idea is, I don't know, we assume it is the safe. This is sort of the large upper bound that is impossible to reach, basically.
As if you had infinite pilots.
Yeah. Yeah.
So the Oracle should do that.
Yeah. Exactly. And as you can see here, we compared our approach with some random pilot assignment, which is fully decentralized. Every user was going to kind of connect to the network, pick some random pilots, which is already known to the access points anyway, and some greedy approach. And as you can see here, we sort of outperformed these approaches by some sort of high margin, and our approach performs as good as the exhaustive search. But
sorry, again, they didn't do repulsive, realistic, or repulsive optimal.
Actually, this repulsive optimal here, the what I'm talking about, this repulsive heuristic. This optimal one is sort of another type of formulation of this problem, which is, I used some other, external libraries for that to implement it. And I've already cited in the papers, but I'm not quite sure how does it exactly work. But okay, here in this plot to the right, we kind of compare it with different number of access points. We have m equal to 100, 200, and 300. As you can see, okay, it's obvious that's increasing the number of access points will increase the rate. This is by the way the cumulative distribution function for the user. And again, our approach works better than random and greedy one. And this table here shows I'm not sure if it is average or the rate for the 95th percentile of the users, 95 likelihood. But anyway, it's kind of performs better than. But here the thing is, by increasing the number of user equipments, number of access points, as you can see, the gap between our approach and sort of this Oracle one kind of decreases. And
what's the table again?
I'm not sure if it's the average rate for the users. Or the 95 percentile. I need to check it.
95 is not, because if you compare the numbers to the graph,
it should be somewhere here, 95 percentile. 5%. Yeah, no, not 95 percentile. For the user. It should be somewhere in here, maybe. Yeah, it's not 95 percentile. Because the average should be, I don't know, somewhere in here, maybe.
So why is the exhaustive search doing worse than the repulsive?
Actually, it's only for, if I'm not mistaken, it's for, first of all, it's for a very limited number of number of realization, basically.
Was it different realizations?
Yeah, it's 100 realization, and I kind of, this is the average for 100 realization. The second one is maybe this is the main reason. Here, maybe this one, this the diversion repulsion score doesn't reflect directly the, I'd say, what do we wanted to do, you know? We need to kind of maximize the rate, but here we are only using the geographical information to increase the rate. This function 100% doesn't reflect the kind of rates. This is probably the main reason. But to create this plot, if I'm not mistaken, I ran the simulation for 500 or 100 or maybe 200 different iterations, and I take the average. It can be one reason because it's sort of average, but it doesn't make sense. I mean, because the realization was same when I was running it. Maybe the other reason is makes more sense.
Sorry. With exhaustive search, then what are you doing?
I'm trying to always find the maximum rate, the sum rate, basically, maximum sum rate here.
Right. So the fact that you have worse result than with the approach in a short range cannot be due to the fact that we are using a different criterion to clusterize the most deepest cost. Probably, as you said, you computing the average over a limited number of iterations.
Maybe, yeah. I thought one of this is
search. You try all possible combinations and you pick the one that gives you the best performance, right?
Maybe that could be the reason. I'm not sure.
Well, if you use the same, if you change realization.
No, realization is the same. Realization are the same. I mean, I generate some realization. I run 3 different algorithms on this realization, and I again generate another one and run.
Yeah, but in that case, you shouldn't observe something like that.
That's true.
Yeah.
Because you are optimizing for something, and if you're optimizing with the food.
Yeah. Maybe. Okay. Anyway, here we can compare our approach with different given approaches for different number of user equipments, while the number of access points and the resources are the same. As you can see, okay, increasing the number of users will kind of decrease the rate, which is something obvious. But again, here the slope of the reduction for our approach is kind of smaller than the other 2. And the other result here, this shows the performance of the different approaches by considering with respect to different pilot lengths, different pilot numbers, basically. As you can see here, okay, by increasing the number of pilots, the rate improves only up to a certain level, and after that it's kind of stop improving or kind of start to decreasing. And yeah, again, when the number of pilots is equal to the number of user equipments, as you can see here, in this point here, our approaches acts as good as the Oracle one, because yeah, we have enough pilot to assign to everyone. Okay, next work, what we thought is, okay, if we kind of formalize our problem in this way, to the right, to the left, this sort of formulation tries to generate small clusters, a small number of clusters with big size. Big size cluster is few big size clusters, basically. And this is not what we want. And exactly, yeah, to solve this problem, we add some sort of normalization term to our problem. Here we are trying to punish the policies that's kind of generate small, few large size, basically clusters. Why we are doing this is, okay, assume, okay, we have a lot of user equipments. They are all the user equipment that are using the same pilot, orthogonal pilot. They are generating basically full interference. And we want to kind of punish them by the number of the links that existed between them. And here again, we kind of comparing the previous one, which here, the number of the pilots was the fixed, but here we let them to grow. And also we propose new algorithms, and then next work kind of speed up the search process, and we kind of compare the result for the uplink and downlink, and we considered the multi-antenna access points instead of having one, and instead of having only one, the location of the users. We assume why not we ignore the location, maybe you use some other information like a CSI or something like this. And in general, we propose this iterative optimal search algorithm, which basically, just like as previous one, it has some initialization phase, which randomly basically assign the users to different pilots to different users, and inside some while it's sort of first applies some big perturbation operator, which means basically this is a sort of search problem. We have to avoid stacking to the local optima. This operator basically take the users, and without considering, okay, some certain moves will increase or decrease the performance, it's move the search space to some other places. And at the end, yeah, it applies some sort of, again, some search process, which here we have not only the exchange move, but only one move, one move, let's say. And at the end, we have some sort of strong perturbation. This helps us to kind of skip the very deep local optimals. And this plots, yeah, shows the uplink and downlink throughput for different number of user equipments, and N is equal to 200, K is 40, and tau P is 10. And here L shows the number of antenna per base station. As you can see here, okay, if we increase the number of L antenna per base station, kind of its rate increases very large, both in downlink and uplink and downlink. This one is the, again, number of, that shows the result for the number of different access points. The result is just like as previous one. I will skip this slides a bit fast to, here is again the results for different one, but as you can see here, I mean, we tried different configurations and different search schemes. As you can see here, okay, most of the time they reach some certain I don't know, threshold, let's say, some certain level. We cannot improve it after that. Even by comparing the previous repulsive one, I mean, repulsive one is also somewhere in here. So it's basically the best performance we can get out of it. And so we thought, okay, we are solving some search problem. What we can do is reducing the search space, or I don't know, or something else. I mean, it's not very smart. It's just searching. We are just sort of sometimes cutting the unusable solutions, or basically reducing the search space, or some approach to speed up the search process. We thought, okay, can't we do something smart, inspiring from recent advances in machine learning and especially deep learning. We thought, okay, can't we define this resource allocation problem in wireless communication in general as a translation problem? And by the translation, what do we mean is something similar to the natural language processing, when we want to translate from Portuguese to English, or this nice image-to-image translation, which here is a very famous data set that's selfish to the anime. And what do we mean by translation in wireless communication is something like this. Okay, assume we have this sort of configuration, network setup, let's say. And the thing is, okay, can we observe this? The question is, can we observe this, all the information we have about the network? This information can be, I don't know, the location of the user equipments, the channel between the user equipment and access points, or location of access points, and whatever we know, the battery level of the device, or transmission power, or everything basically, and kind of translate it to something new, which can be the allocate resource like allocation among the different user equipments, or I don't know, the transmission power for different users, or even both of them combining of these two. And this is what we know, what we call it as a cognition-based networking. And what do we mean by cognition? Okay, just like as translation, language translation, okay, what we do is reading all the text, kind of decoding it, moving it to some certain space, some latent feature space, let's call, and again, decoding it to another, the target language. Here, this is what we think about what we consider as or what we call as a cognition-based networking. The idea seems to be cool, but the question is how we can do it. And basically, again, this cognition-based networking is some sort of, we can call it a representation problem. We tried several different approaches. This is a problem, which is the title of my PhD, basically. And we tried from the beginning, I tried different ways, for example, restricted well-span machine or autoencoder or some sort of layered convolutional neural network. And I mean, even I went for graph neural network to kind of model this, to understand all the information basically that has existed in the network and learning something and decoding it to some other space, but they weren't successful enough. What do we want is something like this, having some decoder and encoder architecture or systems. This is one we tried. I mean, actually, this is not our work. Some from somewhere else. We wanted to kind of use autoencoder to reach this cognition. Basically, I wanted to do this repulsive clustering thing using this autoencoder, where we kind of learn some, move the, I'll say our information to some latent space and use this information here to do this clustering part. But it wasn't successful when we wanted to kind of apply for repulsive clustering. We couldn't kind of define appropriate loss function that is differentiable, and it doesn't work at the end. But when I came here to Zurich to start my secondment with Fernando, we thought, okay, this transformer architecture can be a good, I mean, solution for some problems like this. Transformers introduced back to 2017. They are basically a stack of some basically multi-head attention networks followed by some feed-forward neural networks. And yeah, this is basically the whole architecture. And for example, this is the basic transformer paper. Here, as you can see, okay, there is some encoder and decoder. What they are, the architecture are the same, but here what we have is beside that, the other two layer is some masked multi-head attention layer, which is mostly, I mean, originally introduced for NLP tasks, not something else. What we are interested in is something like this, some architecture like this, which is basically a vision transformer, which introduces it to image classification, basically. What happens is it kind of cuts image to different patches, and these different patches go through some linear projections, and at the end, okay, we have information about the position of the patches. And again, the transformer encoder is something like this. And at the end, I mean, here they have some, the class token. This class token is a representation of the whole image. And at the end, they use this class token to do this classification. But what we have in my mind is, again, using some sort of similar architecture here, we have different features from different user equipments. It can be location, I don't know, location or I don't know, channel state information, the distance between the user with some other user equipments or the base stations. But here, unlike the previous one, we do not have any class token or something. We kind of want to translate. Our task is basically some sort of similar to image-to-image translation. We want to kind of do the prediction for every single token we have. Here, the token kind of represent the features of the user equipment, different user equipments. And the reason we choose transformers is, first of all, they can kind of handle the long-range dependencies as well as the short-range dependencies, because all the informations here go throughout the transformer. It gives this opportunity, unlike the, for example, convolutional layers, which only kind of considers the local short-range dependencies. And another approach, another advantages is interpretability. Here, because of this attention layers, thanks to this attention layer, our agent, our model can learn, okay, if for example, comparing to blind or conventional optimization schemes, when you want to kind of optimize the rate for some users, what you do usually is, for example, picking some user which minimum rate, you kind of increase the power for this one, but increasing this power will kind of reduce the rate, for example, for the other users that are nearby. But here our agents, thanks to this attention mechanism, can learn, okay, if I increase the rate for this one, the power for this one, I may kind of affect other users. Another thing is the scalability. You can kind of train this model for fewer number of tokens, basically, and then easily extended. And another thing is, another good thing about transformer is unsupervised training. This is easy unsupervised training for vision or NLP tasks, but we haven't found some ideas likely to do the unsupervised training on our specific tasks, but it's general there. And what people usually do is they train on a very large data sets in an unsupervised way and kind of fine tune it for a specific task in a sort of supervised way. This is still a work in progress. I tested for very small scenarios and they are working fine. I mean, comparing to the heuristic I showed. But what we kind of expect at the end is interpretable and cognition-based network optimization. Probably, I hope very soon you can find some output of this work on the internet. Okay, thank you very much. Any questions?